In this video, I'm connecting a real ultrasonic distance sensor to my Raspberry Pi for the first time and writing ROS nodes for it in C++. I've never done this before, so we're figuring it out together. By the end of this video, you'll have working ROS nodes working out real-world distance measurements with an LED that indicates it all. We're going to use a Raspberry Pi 5 with Ubuntu 24 running ROS, an ultrasonic distance sensor and LED, and we'll be writing C++ nodes that read the data, then publishes and subscribes to a ROS topic. To get started, we will need to wire all the components together and then wire it up to the Raspberry Pi using its GPIO pins. We're going to need 3 female-to-female jumper wires for the ultrasonic sensor, 4 male-to-female jumper wires for everything else, 3 1K resistors for the echo pin, which I will get to later, and 1 150 to 500 ohm resistor for the LED. Then finally, we will need 1 LED, preferably red, but it does not matter. First, connect the 3 female-to-female wires to the pins of the ultrasonic sensor, labeled VCC, trigger, and ground. The other end of the VCC connected wire should go into physical pin 2 for a 5-volt power supply. Then the other end of the trigger wire should go into physical pin 16, also known as GPIO 23. Then the other end of the ground wire should go into a physical pin 6, which is a ground pin on the Pi. Now for the most important part. Please make sure you get this correct or it could lead to you damaging your Pi. We are going to connect a male to female wire to the echo pin on the ultrasonic sensor. But instead of directly connecting the other end of the wire to the Pi's GPIO pins, we are going to connect it to a line on a breadboard. For this next part, we're going to need 3 1K resistors. From the first line, where the other end of the echo wire is, connect a resistor to it, so the other end of the resistor is now on another line of the breadboard. Then connect a resistor from the same line as the end of the first resistor, so that the second resistor's end is connected to another line. Finally, connect the third resistor to the line of the second resistor and connect the third resistor's end to a ground or negative of the breadboard. Now, we're going to need a male to female wire. We're going to connect this to the line of the end of the first resistor and the beginning of the second resistor. The female part of this wire should be connected to a physical pin 18, also known as GPIO 24. Next, we are going to wire up the LED. We are going to need another male to female wire. Connect the female end of this wire to the physical pin 12 on the Pi, or also known as GPIO 18. Then we're going to connect the other end, the male end, to a line on the breadboard. On this same line, we're going to connect the resistor of the LED, which could be from 150 to 500 ohms. The beginning end of the resistor should be on the line of the wire. Then the end of the resistor should be on another line of the breadboard. On this line, we're going to connect the positive end of the LED, the longer side, or anode, to the same line of the end of the resistor. Then the shorter side, or cathode, to the negative or ground rail of the breadboard. Finally, we're going to connect the last male to female wire from the negative or ground rail of the breadboard to physical pin 14, which is a ground pin on the Pi. We are finally done with the wiring of the components. Now let's get straight into the programming of the nodes. Now let's create a ROS package for our distance sensor node. We include the required dependencies, RCL-CPP for C++ ROS client integration, and std-msgs for standard ROS message types. To get started, we will need to import everything we need for this project, which includes chrono for precise time control, memory, which gives us access to smart pointers in C++ that automate memory management, thread, to allow for multiple things to run at once, RCL-CPP, std-msgs, and GPIO, which is a library that allows us to use the GPIO pins on the Pi. To trigger the ultrasonic sensor, we set a 10 microsecond high pulse. So we set the trigger line to high and wait for 10 microseconds. Then we set it back to low. We need to measure how long the echo pin stays high. That duration corresponds to the distance. So we use the formula. Distance equals time multiplied by speed of sound divided by 2. We divided by 2 because it's a round trip. So we need to calculate the distance of going one way. Next, we need to publish the distance over the ROS topic. We publish to the topic this topic, which publishes into the flow tab with a queue size of 10. Now we move on to the LED control file. We will need to import everything we need for this file, which includes RCL-CPP, std-msgs, and GPIO. In this C++ file, we subscribe to the this topic. and calculate whether the distance is below the desired range of 20 centimeters. And if so, we turn on the LED and display the exact distance on the screen's console. Next, we need to add the required prerequisites that are needed to make CMake compile our C++ code correctly. We make sure to add the additional dependency GPIO CXX lib. Now we need to add both C++ files and attach them to their target dependencies and their target library GPIO CXS lib. Finally, we need to tell CMake where to put the compile files. We're almost done. Now we just need to build and run the compiled code. First, let's compile using the colcon build command. Now we have to run both of the compile code. With two terminal windows open and components connected to the Pi correctly, let's run them using the ROS2 run command. You should now see the LED and the ultrasonic sensor doing its job properly, displaying the accurate distance of the object in front of it. If it gets too close, the LED turns on. If you're trying to make this project for yourself, here's some problems you may have faced and how to fix it. If you're using a code editor like VS Code and you get sourcing errors with the imports, make sure to right-click and edit the include path setting. This should fix the issues immediately, but if not, make sure to scroll down and add the ROS2 path to the include section. Another problem you may face is build errors. If you get these errors, make sure to check cmake list.txt. Check if you have got everything exactly correct, but if so, possibly you don't have GPIO library installed, but you can do that with the command on the screen. Now, we have real hardware publishing into ROS using C++. That's the foundation of ROS. If you have any suggestions on what sensor we should try next, leave a comment below.